Anybody want candy? Alrighty. Well, I've been told I look like Mr. Incredible, so I decided to play it up. Well, I used to have a real tiny car. I don't think that's not really true anymore. But does anybody have any questions about anything before we start? Nope. Okay. So today we're going to learn how to write Lewis structures, and it's more than this today. We'll have a lab on this as well. But here are the steps, and there's lots of words there. Let me give you the breakdown. The first rule is write down the correct skeletal structure for the molecule, which I've abbreviated skeleton. Write the skeleton of the molecule. So one of the hints, the bigger and or least electronegative atom tends to be the center. So we're not going to do the big ones, just the long organic molecules. We're not going to do that really for this class. We're only going to do really small ones. So in general, the bigger atom and or the most electronegative atom is usually the center. Sum up the valence electrons. So calculate the number of electrons to Lewis structure by summing the valence electrons for each atom in the molecule. So sum up the valence electrons. Then step 3, put octets on the atoms on the outside, or duets for hydrogen, if you will. And then add double and triple bonds as needed to get to a proper octet. And then minimize the formal charge. It's not listed in this rule, but you find about this later. The general trend, if you didn't know this before, hydrogen and the halogens tend to form one bond. Oxygen and sulfur tend to form 2 bonds. Nitrogen and phosphorus tend to form 3 bonds, and carbon tends to form 4 bonds. Now the word is, of course, tend, and as the students in my office hours complain about why have a rule when we have 1,000 different exceptions to the other rules. So yes, there are going to be some exceptions to these rules. But this is the general trend. And out of curiosity, who had chemistry in high school? So okay, so half the class. That's good. So did you do Lewis structures? Yeah, okay. You probably used this trend. Didn't do any of the complicated ones. And another topic, so I guess I should start off by saying that Lewis theory is wrong. It's not the reason why things bond. Things bond because low energy and the structures they form is, well, later on we'll learn about molecular orbitals. They form new configurations based off of the fact that lower energy has to deal with the electronic magnetic fields of the nuclei and electrons surrounding the atoms. But Lewis theory, and it's a very useful theory. It's fundamentally incorrect, but we use it quite a bit. In fact, you can look up the Lewis structures for anything. Whenever I have to take a drug, I always look up the Lewis structure because I'm allergic to sulfonamide drugs, and I can tell by the Lewis structure if I'm going to be allergic to it or not. So you can still use it. So and the next thing, a concept of resonance. Sometimes there's more than one kind of Lewis structure that can be formed. So well, Lewis thought it was just like a music term, resonance. So for instance, ozone can be written like this. Maybe I'll zoom in. You can see this a little better. Ozone can be written like with a double bond on the left or a double bond on the right. So which one is the correct Lewis structure? The idea is they both are, and then it forms a combination of the two. Kind of like if you have two purebred dogs, you get a mutt kind of thing. Same idea with that. You have these two meetings as a blend of the two. So we'll cover this more later. So let me do a couple examples. Write the Lewis structure for the nitrate ion. Include resonance structure, so nitrate. So we have NO3 minus. So the first step is to write the skeletal structure. So which atom is bigger, nitrogen or oxygen? It's nitrogen. It's to the left of oxygen. Nitrogen is in the center, and we're going to have oxygens around it like that. And now we sum up the valence electrons. So where is my table? There we go. Nitrogen has 5 valence electrons. 1, 2, 3, 4, 5. And oxygen has 6. 1, 2, 3, 4, 5, 6. And the students at home that are listening to me, I'm just counting over from the left. You can also look at nitrogen has 5A on top of it, and oxygen has 6A. Those are the number of valence electrons. So does everyone see where I'm getting the valence electrons for nitrogen and oxygen? Okay. So summing up the electrons, we have 5 from nitrogen plus 3 times 6 for the oxygens. There's 3 oxygens. Then plus 1. The plus 1 comes from the -1 charge. So that's just 4 times 6. That's 24. So we have 24 electrons. And each line is 2. Okay, so I've already placed 3 lines, so we've placed 6 electrons. So the next step is, so write the skeletal structure, did that, sum up the electrons, did that. Now we gotta place octets on the outside atoms. So we have 6 electrons placed with the 3 lines, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now we've placed all 24 electrons. The next step is add double and triple bonds as needed to get an octet, to have everything get an octet. So the goal here is everything to get 8 electrons. Each of the oxygens, they have 3 lone pairs, 6 electrons, and then a bond, so that's 8. Nitrogen, though, has only 6 electrons, 2, 4, 6 for, so 6 electrons that it's sharing. So nitrogen needs 2 more. And what you can't do this. You can't say, all right, there you go. That would be NO3 minus 3. We don't have that many electrons. So can't do that. But what we can do is we can add a double bond there. Why double bond there? Why don't I add one instead? Why don't I add one here? That one's good. Why not add it there? And of course the answer is I can add that too. Why do it there? Oh geez, I'm gonna run out of space. Why do it there when I can add one there? So now this is where I have the resonance structure. So I have 3 different structures. Also, what's common if something's an ion, to put the thing in brackets and then put the charge of the ion on the outside. I'm running out of space. I'll just, you know what I'm going to do? I'm just going to take over the other side. And then you have these double lines here like this saying that so here are the different resonance structures. Okay, so how did I get this? Well, so Lewis structure for nitrate ion NO3 minus, so 1 nitrogen, 3 oxygens. Put the biggest and or least electronegative atom, which nitrogen is for both, in the center. Did that. Then place the oxygens around. Sum up the electrons. We have 5 for the nitrogen, 6 from each oxygen, and 1 from the -1 ion, 24 electrons. We place them all on the outside. And after that, oh wait, I forgot to. When you add the double bond, I missed something. When you add the double bond, you have to erase one of the lone pairs. Sorry about that. So this oxygen here then decided it can share electrons with nitrogen. Also, this oxygen here can share electrons with nitrogen, and this oxygen here can share its electrons with nitrogen. So, but all three are the equivalent. So then we say that it's a resonance structure, it's a blending of all of them, and then the bond is kind of like 1 1/3 of a bond. So it's not a single bond or a double bond, it's sort of like a 1 1/3 bond. And that's Lewis there. Here's a prettier picture of it if you want like that. And that's kind of how it really is. In real life, it does form an even bonding scheme along all of them. So this is, of course, the case where Lewis structure gets its spot onto what it is in real life, too. So can you tell me what the proper Lewis structure is for hydrogen cyanide? And the hint here is to count the number of electrons. Hydrogen has 1 electron, and carbon has 4, and nitrogen has 5. So there are 10 electrons there. How many people think it's A? I think it's B. I think it's C. I think it's D. All right, so people are going for D. D is the correct answer. So D is correct, and that's the one that has 10 electrons if you count them up. A. Option A, there's 2, 4, 6, 8, 10, 12 electrons. So this would be a -2 ion. This is proper for a -2 ion. This one has only 8 electrons, and it also has a double bond to hydrogen. Hydrogen tends not to double bond with things. It actually, I don't know of any cases it does. Hydrogen can bond with more than one thing, but it tends to be rare. So boron hydrides, they can bond with more than one in that. And there's also a molecule H3+ that has multiple bonds, but it's rare that hydrogen engages in more than one bond. This one is also proper, but this has got 14 electrons, and this one is proper for the neutral molecule. And it also follows the other rule. Hydrogen tends to bond with 1, carbon tends to have 4 bonds, nitrogen tends to have 3 bonds. So this fits that rule too. Man, where is everybody? Only 5 students in class today. Halloween, huh? All right, so now I mentioned formal charge. Formal charge, here's the whole definition in the book. So formal charge, and then so to calculate formal charge, you look at half of the bonding electrons and all the lone pairs. That's pair. You look at half of the bonding electrons and all the lone pair, and then compare it to its original number of electrons. I must have wrote this quickly. Okay. And to give you an example here, hydrofluoric acid. So look at and of course a single bond is 2 electrons, so 1 electron goes to hydrogen, 1 electron goes to fluorine. So hydrogen would have 1 electron. Fluorine is going to have 1 electron from there, 2 from there, 2 from there, 2 from there. So fluorine has 7 electrons. Hydrogen starts out with 1 electron. It has 1 electron. Its formula charge is 0. Fluorine starts with 7, has 7, formal charge is 0. So formal charge is 0 for both of these. So let's look at this. Assign formal charges. We have the cyanate ion, OCN minus, which resonance structure is most likely to be the correct structure. So, and I've kind of enhanced this already. So we have OCN with a single bond, oxygen single bond to the carbon, carbon triple bonded to the nitrogen. So that's one possibility. Possibility B is oxygen and nitrogen both double bonded to the carbon. And option C, oxygen is triple bonded to carbon and single bonded to nitrogen. So those are our 3 different possibilities. So let's start off with oxygen, and I apologize if there's anyone colorblind on here, but I've labeled oxygen as blue, and notice that oxygen has 3 lone pairs, 6 electrons, and gets 1 from the bonding group. So it has 7 electrons. So if you come in late, you gotta eat candy. So oxygen has 7. It starts off with 6. Therefore, it has an extra electron, has a formal charge of -1. Does everyone get that? Anybody have any questions? Why it's what, -1? You have a question?
Can you repeat that?
Okay, of course. So formal charge, you look at so the atom keeps all of its lone pairs and gets half of the bonding electrons. And then you compare those electrons that it has, compare it to what it originally has. So oxygen, for instance, what do I mean by original? Oxygen has 6 originally because it's got 6 valence. Fluorine has 7, neon has 8, nitrogen has 5, carbon has 4, and so on. So and that's what I've written up there in the colors. Oh, geez. So repeating again. So oxygen, the number of electrons that oxygen gets for the formal charge, it has 6 from the lone pairs, 2, 4, 6, and then 1 bonding. So it has 7 electrons. Starts off with 6. It has 1 extra electron, so we assign it a -1 charge. So, good? Okay. Carbon, 4 bonding, so no lone pairs. So originally has 4, now has 4, 0. Nitrogen has 2 from lone pairs and then 3 from bonding, so 1 from each of the triple bond. Has 5, started with 5, formal charge 0. All right, so option B, we have Oxygen has 2 lone pairs, so 4 electrons, and then 2 bonding electrons, so 6 electrons. Starts with 6, has 6, formal charge is 0. Carbon, 4 bonding, same as last one, starts with 4, 0 formal charge. Here, nitrogen has 4 bonding, 4 lone pairs, 2 sets of lone pairs, 2 lone pairs, and 2 bonding. So 6 electrons, start with 5, has a -1 formal charge. And then here, option C, oxygen has 2 from lone pairs, 3 from bonding starts, so it has started with 6, has 5, formal charge +1. Carbon, same, 4 bonding, starts with 4, formal charge 0. Nitrogen here has 6 from lone pairs, 1 from bonding, so it has 7, starts with 5, formal charge -2. So the last step is we got to minimize the formal charge. And looking at these, we know right away that C is out because we have a -2. So now we have to pick between the -1 charge being on the oxygen or the -1 charge being on the nitrogen. So which one do we pick? We pick the one that's more electronegative. Oxygen is more electronegative than nitrogen. Therefore, the most proper structure is this one, number A, because it puts the -1 charge on the more electronegative atom. So, questions with how to do this? All right. Let's see if you can follow. What is the formal charge of the central oxygen atom in ozone? And to make it easier on you, I have written the structure for ozone. There's a resonance structure, but either way. Here is the Lewis structure, or one of them, for ozone. And oxygen starts off with 6 valence electrons. So what is the formal charge? Formal charge is half the bonding and all of the lone pairs compared to the original. So how many lone pairs does it have? And then how many bonds? Each bond would indicate 1 electron from each of the bonds. How many think it's A? 0. How many think it's B? +1. How many think it's C? -1. I think it's D? -2. So I'm going to come and talk to you guys real fast. It's +1. So, but. Are you guys following? Okay. Yeah, right now, so 1 from each of the bond. Oh, why is this one proper? Yeah. Is there anyone else who can draw? That's a verify. That's also So one of the questions was why draw the Lewis structure that way? That's the only one this is the most proper Lewis structure. It's the only one that has all the octets, and it also minimizes the formal charge. So, but it's +1, and it's another reason why Lewis theory is wrong, because ozone forms a bent structure, and it's kind of like a boomerang. It's very even. Okay. So, and I'm hoping that you can just watch me do Lewis structures over and over again, and hopefully you can start to learn how it's done. You will have homework on this, and like I said, we'll do some labs. But now it's time for you to watch me do stuff. So, there are some exceptions to the octet rule, and one of them are known as free radicals. Maybe you've heard of free radicals. These are from odd numbers of electrons. So nitrogen monoxide, for instance, and nitrogen dioxide, these are both free radicals. So for this one here, I'm just going to make my pen smaller. Nitrogen is going to have 5 electrons and then 6 electrons from the oxygen, so we have 11 electrons to place. So we have nitrogen attached to oxygen. This one's skeletal structure is easy. So we have 2 electrons placed, 2, 4, 6, 8, 10, 11. Now let's look at this. Maybe I should make the dots bigger. Actually, I can make them bigger. So we placed all 11 electrons, but so oxygen has an octet, nitrogen has 2, 4, 5. That doesn't work. So what's going to happen is a race to give it a double bond, like that. And this is, now let's look at the formal charge of these. Formal charge, nitrogen starts with 5, has 1, 2, 3, 4, 5. Formal charge 0. Oxygen starts with 6, oxygen has 1, 2, 3, 4, 5, 6. Formal charge 0. So that's really the hint. When you find a formal charge of 0, you probably have the best Lewis structure, and or at least a stable form, and you can have what's called an isomer, so same number, different connectivity. So this is going to be the best Lewis structure, but there's an odd electron. Another reason why I place it on the nitrogen, because it's less electronegative than oxygen. Why don't I move an electron over there? If I did that, I would give nitrogen a +1, a -1, and oxygen a +1. So that wouldn't be as proper. So that's the Lewis structure for nitrogen monoxide. What about NO2? Nitrogen has 5, plus we have, oh wait, we have 2 oxygens. And then we have 2 times 6, so we have 17 electrons. So place octets on the outside. So we've already placed 4 electrons. 6, actually let me make the dots bigger. Oh, that's too big. 6, 8, 10, 12, 14, 16, 17. So oxygens all have octets. Nitrogen has 5. That's not good enough. So what do? We erase 2 and give it a double bond, and then we give it a resonance structure. Actually, maybe I'll put it below. So we give it a resonance structure. Oh, wait a second. What do I do? Oh, forgot to the double bond. There we go. Give it a resonance structure, and then noticing that there is an odd number of electrons. So what? Why do we care? Free radicals tend to be extremely reactive. So free radicals are very reactive, and as such, they can help propagate chemical reactions. A chemical reaction that many people are concerned about is fire. So has anyone ever heard of the fire triangle or fire tetrahedron before? So some people have. Okay, so if you are studying firefighting, there's two things they'll teach you. The old one was the fire triangle. And the triangle is fuel, oxygen, and heat. So if you want to put out a fire, if you remove any one of these, the fire will go out. So let's say I've got a campfire. And if I just let the campfire sit and all the wood burns out, the fire's going to go out. No more fuel. So when the fuel leaves the equation, fire stops. I can also smother a fire. I can, if like a candle, if you want to put out a candle, put a glass jar over it, the candle will eventually burn out because it burns out all the oxygen. And then the last one, heat. So you probably know you can put out a fire by throwing water on it. So what happens when you throw water on a fire? What is that? That's steam. It's taking the liquid water, turning to steam. That takes energy. In doing so, takes all the heat away from a fire, puts the fire out. Then the fire tetrahedron is the same thing, although frequently oxygen is replaced with oxidizer. So you can have fires like we just saw last class. You can have a fire using chlorine gas. So fluorine and chlorine can be oxidizers as well. And then the last step is a chain reaction. So you can stop a chain reaction to put out the fire. And halons, so a firefighting technique called halons, an extinguishing media called halons, they are chemicals that have halogens in them, hence the word halon. And the halons, when they heat up, they release halogens, and the halogens act as electron scavengers, they say. They go after these free radicals, and then they put out the fire that way. Has anyone ever seen one of the best movies ever made, Terminator 2? So, yes. I'm glad everyone still thinks it's one of the best movies ever made, behind Braveheart, of course. But Terminator 2, if you remember, when they're in Cyberdyne Systems, when they have an explosion, they're like, it's the halons! And the halons come down. They can't breathe except for Arnold, right? Arnold's the Terminator. He doesn't need to breathe. But they all grab gas masks. So, halons, they'll smother you. They'll suffocate you, I should say. You can't, you can breathe them in, but they displace oxygen. So, all right. So, odd number of electrons. The other so another exception is incomplete octets. So, boron trifluoride and aluminum trichloride are both examples. So, boron trifluoride. I'll make it a little bigger again. So, boron trifluoride, and I'm going to draw it this way. So boron trifluoride, boron has 3 electrons, and then there are 3 of them. So fluorine has 7, 21, 24 electrons. So where am I getting these numbers? Just to make sure everyone understands, boron is 3 over in period number 2. 1, 2, 3. Fluorine is 7. So 3, 4, 5, 6, 7. So those are the numbers of electrons. So that's where I'm getting the 7. 3 times 7 is 21, plus 3 is 24. So we've placed the line, and boron is the biggest and the least electronegative atom. It's in the center. And so we place 6. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now we've placed them all, and you're like, all right, now I can add a double bond to boron. And it turns out that boron does not double bond with fluorine in this case. It just leaves it like this without the incomplete octet. So boron here just is happy with 6. I shouldn't say it's happy. It's very reactive. This is actually a very reactive molecule, but it stays incomplete. So boron and aluminum can both form incomplete octets. And you're like, aluminum's a metal, and chlorine's a nonmetal. They should have an ionic bond. Nope, Metals can covalently bond. And this is actually really just the same as the other one. Aluminum is going to have 3, and then chlorine is a halogen. It also has 7. So we have 24 electrons. Aluminum in the center, 3 Cls, and then placing the electrons as such. There we go. So now we have aluminum trichloride, and just like boron trifluoride, stays with the incomplete octet. And this is also highly reactive. It's actually a very good blood coagulant too. So if you ever have a cut and they put something on it and the bleeding stops immediately, it's aluminum trichloride. So, okay. How are we doing? Questions with this? Now we have expanded octets. This happens for things only with period 3 and beyond. So what do I mean by period? A period is a row on the periodic table. So periodic table, a period. Then the periods, you can see, are here on the left. Period 1 is hydrogen, helium. Period 2 is lithium to neon. Period 3 is sodium to argon. So only the elements in period 3 and beyond can have an expanded octet. And the reason for that is because the d orbitals need to be utilized to have this happen. The d shell is where the expansion happens. And so this is the 3s and the 3p. The 3ds are here, but they're empty. So phosphorus is going to have so 2 electrons in the 3s, 3 in the 3p's, and 0 in the 3d's. It still has empty orbitals that can be used. So nitrogen above that is going to have electrons in the 2p. There is no 2d. So you have to wait till the third quantum shell to have that happen. So only period 3 and beyond can expanded octets happen. And is it, okay, good, didn't blow up. Phosphorus pentachloride. So we have 5 electrons from phosphorus plus 7 times 5. There's 7 from each chlorine, so 35. We have 40 electrons here. And then we have phosphorus in the center. And then we have chlorines around it like this. I'm actually drawing it purposely this way because we'll find next chapter that this forms what's called a bipyramid. So a trigonal planar bipyramidal structure. Okay, so I've placed 5, and I've placed 5 lines, so 10 electrons. So I've placed 10 electrons, I need 40. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay, all 40 electrons. Each of the chlorines has an octet. Phosphorus has 10 electrons. It has its expanded octet by 2. So instead of 8, it has 10 electrons. And since phosphorus is above period number 3, it can do that. And then sulfur hexafluoride. So we have 6 from sulfur plus 6 times 7 for the fluorine. So 6 times 7 is 42 plus 6 is 48 electrons. Then we put sulfur in the center. And we have 6 fluorines around it. So I've put 6 lines. That's 12 electrons. 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. Good. All right, I'm always nervous that I'm going to miscount somewhere. So 48 electrons around that end. as we'll find out next chapter, this forms what's called an octahedral structure. So with all those bonds there. So and sulfhexafluoride is an interesting molecule because we use it as part of our stealth technology. So our stealth technology is threefold. We have so the materials that they make the stealth fighters out of, it just absorbs the microwave radiation. So the way radar works, so you have a plane, you shoot microwaves, hits the plane, comes back, you detect it, and from the time delay, and you have enough of these going, you can figure out the position of the aircraft. So that's how you find a radar signature. I mean, you can tell if where an airplane, boat, or whatever it is you're looking at is. So first part is we have materials. We make the aircraft and or whatever it is. You can have boats. The materials they make out of, they absorb microwave radiation. And they're layers. There's different layers of them. What the layers are not classified, but the thickness of the layers is classified. And also the angles of the aircraft and or marine craft, they are shaped in such a way that when the radar, so if you've seen the stealth bomber, it's very angular. So when the microwave comes, so the angle's like this, the microwaves come, it shoots off the other direction. So it doesn't get reflected back to the source, it gets reflected off out into space. The Raptor fighter, it's more curved. So we don't use the angles as much, we use more curve. The last part of our stealth technology is our fuel. And what we have in our stealth fighters is very cleanly burning fuel. So maybe you've heard of heat-seeking missiles before. What is a heat-seeking missile? It's actually a radar. It's really radar lock. It's not really looking for heat. It's looking for the exhaust. So when you burn jet fuel, it makes soot. There's hot soot particles, and that's really easy to see on radar. So actually that's more frequently you track the soot trail of an aircraft rather than the aircraft itself. So what we do is we put lots of sulfur hexafluoride into our jet fuel for stealth fighters. So when it burns and it's really hot, fluorine pops off, and then that's the same thing as a halon. It's an electron scavenger. It stops a chain reaction, and it prevents soot from being formed coming out the back of an aircraft. So that is our last part of our stealth technology there. And it's funny looking at pollution charts. You'll see sulfur hexafluoride in the atmosphere, and the other countries will be like, so United States, why is there sulfur hexafluoride in the atmosphere? And we're like, we don't really regulate sulfur hexafluoride, kind of thing. It's because we use it on our stealth fighters. If they see it, they know that we've flown there, basically. If they see the sulfur hexafluoride, it's also really heavy. So I think they have the picture. Do I have that? Let me see if I have the in action. Is that with sulfur, with fluorine? Yeah, here we go. Here's sulfur hexafluoride. So it's really heavy. And so when we fly the stealth fighters up above, the leftover SF-6 does fall down. And so if people find it, they're like, well, where did all this come from? So there you go, sulfur hexafluoride. I guess I used to live in Oahu, and this was very common. Have you ever seen the big golf ball looking thing in Pearl Harbor? Has anyone ever seen that? They have this, it's the Advanced Radar Tracking Station. It looks like a golf ball on stilts. And sometimes it's in Pearl Harbor. What that can do, it's a very, very powerful radar station, and it can track something the size of a softball. And why do I care what's big about a softball? I mean, so it can track a lot of things, and it probably knows where all the albatrosses are on the Hawaiian Islands. But what if you saw a softball moving at 500 miles an hour over the Pacific Ocean for 1,000 miles? Is that a softball? No, that's a stealth fighter. So you can track them. They just have a much smaller radar signature. So we not only are we making stealth fighters, we're also trying to figure out how to track them. But it's hard to track them. They're not easy. And one of the stories, the engineers that made it, they did such a good job in making it stealthy. When they did some test flights, they had a hard time guiding the stealth fighters back in because you can't see them on radar. Like, where are you? You know, I don't know where you are. You're a stealth fighter. You know, we can't track you. So they actually have flaps that they can open up. So like, oh, there you are. So then like, okay, you know, this is where you can land, kind of thing. Because if there's bad weather, I mean, how else, you know, you can land with your instruments, and if you're invisible, you can't have your instruments work. Okay, well, so let's write some expanded structures. So there's another one. Write the Lewis structure for xenon difluoride. So xenon difluoride, how do you do this? So xenon is here, and fluorine is here. Oh, I can count for the students at home. So fluorine has 1, 2, 3, 4, 5, 6, 7. And also note that there's a 7A there. And xenon has 8. And note that we have the 8A there. So the valence electrons. So xenon difluoride, we have 8 plus 2 times 7. So 14 plus 8 is 22 electrons. And which one, how do we pick? Xenon is by far the biggest atom. And then we put the fluorines around it. So I've placed 4 electrons, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So that's how I would do the Lewis structure for this. And xenon, since it is above period 3, you can have an expanded octet. So that's why I put the extra electrons around xenon. And it's fine. And next chapter we'll find out that this is a bipyramidal electronic structure, and it's a linear molecule. So, does anybody have any questions on how I've done this? Okay. So, now I'm going to change topics and talk about average bond energies. So, now I've used this example before, kind of like how easy it is to break up with your partner. You know, the more bonded you are with a partner, the harder it is to pay someone to like, I'll never see you again, kind of thing. Like, you know, I don't know. So if you don't like someone, like, sure, $10, I'll never talk to you again. You know, if you've been together for 6 months, like, I'll do it for 100,000, you know, kind of thing. So instead of money, the more bonded two or more atoms are, the more bonded they are, the more energy it takes to rip them apart. So you need to put an energy investment to be able to rip things apart. And here are, we've taken all of the molecules, took a bunch of molecules, and then averaged up the energy it takes to rip them apart. And that is what we come up with are these numbers here. And average bond energy, so let's, for instance, look at, here's a molecule, 2 molecules. If we look at the energy it takes to break these carbon-hydrogen bonds, so actually this hydrogen is easier to break, I'm sorry, it's the other, this hydrogen is easier to break than this hydrogen. So it would be much easier to rip off this hydrogen off of methane than it would be methanol. Why is that? Because this oxygen here, it draws electron density towards this atom, and it weakens this bond. Actually, this bond here is weaker than that bond because of the oxygen drawing the electron density toward it. So this would take a little less energy to break. But we've averaged all of them and just came up with this hydrogen-carbon bond being about 414 kilojoules per mole. And again, this is an average. And our heat of reaction is going to be the amount of energy it takes to break the bonds minus the energy of the bonds forming. So it takes energy to break the bonds, and when the bonds form, energy is released. So that's just the thermo properties, right? So putting energy in the system is positive direction, energy leaving the system is a negative direction. So energy put in the system of the bonds broken, energy leaving the system as the bonds form. So let's look at this for using the steam reformation of methane. And one of the few times the book actually has something that's proper. This is how we make hydrogen. So what is the bond energies? You use the bond energies to calculate delta H. These Lewis structures are much easier. So methane, carbon has 4. Let me do each of the, I'll just really explain it down. Carbon has 4, hydrogen has 1, so we have 8 electrons. So methane, put carbon in the center, and I've placed a single bond to each of the each of the hydrogens, and I have 8 electrons to place. I've already placed 8 electrons. Hydrogen only needs a duet. Carbon has an octet. We're done. That is this Lewis structure. Then water, we have 2 times 1 for the hydrogen plus 6 for the oxygen. So we have oxygen, hydrogen, hydrogen. So this we have 8 electrons. So we've placed 4, and hydrogen only needs a duet, so 6, 8. So oxygen has an octet, hydrogen has a duet, it's happy. So we have 2 of these. And we go to 4 hydrogens. Actually, what am I doing then? Hydrogen is just single bond, like this. And then carbon dioxide, carbon has 4, oxygen has 6. So we have 16 electrons. 2 times 6 is 12, plus 4 is 16. And so we have carbon in the center. So we've placed 4, 6, 8, 10, 12, 14, 16. Now we place the outer electrons. Now we have to add double and triple bonds to add the octets in the middle. And carbon needs to have a double bond, needs to have the octet. And then we have it this way. And why the double bond? Well, you could do this and a triple bond, but then oxygen is going to have a formal charge of -1, and this one have a charge of plus 1. That's not going to happen. So having the double bond like so is fine. And where you put the lone pairs, it doesn't matter. I mean, as long as it's around the oxygen. I mean, I could put the lone pairs like this, and that's fine. Okay, so that's the CO2 molecule. Okay. Is everyone good with the Lewis structures, how I've done that? These are considerably easier as well. And they all fit the carbon bonds with 4, oxygen bonds with 2, and hydrogen bonds with 1. Okay, so now we have to do, by the equation, the sum of the bonds broken, so that's broken, minus the sum of the bonds formed. And this is the bonds are broken are the ones that are, so broken, it takes energy positive, formed, it releases energy negative. Okay, so what are we breaking? we are breaking 4 carbon hydrogen bonds, and I'll color code this. And apologies to anyone who is colorblind. And we're breaking 4 oxygen-hydrogen bonds. And I'll leave blue for this. And we are subtracting 4, we're forming 4 hydrogen-hydrogen bonds. Plus 2 carbon double bond oxygens. I'll do green. Actually, it's Halloween. I should do orange. Because that's too close to red. Oops. But that's my pen. Can you tell the? I guess you can tell the difference. Okay. So 1, 2 there. So you see each of the ones that we're breaking and forming. Now we just have to go to the chart and get that. So hydrogen-hydrogen is 436. 436. What is oxygen-hydrogen? 464. What is carbon-hydrogen? 414. Okay. If you see here, it's telling us 799 in CO2. I'll probably just go ahead and use the 799. Why not? So we have 4 times this plus 4 times this minus 4 times this plus 2 times that. That equals. Okay, calculator. Equals positive 170 kilojoules per mole reaction. Like so. Okay. So when you get a problem like this, it's probably best to go through and write the Lewis structure. So recap with this one. What's the delta H for this reaction? We can estimate it using average bond energies. And drawing the Lewis structure, we're breaking 4 carbon-hydrogen bonds, 4 oxygen-hydrogen bonds, and we're forming 4 hydrogen-hydrogen bonds and 2 carbon-oxygen bonds. And we find out then that the average bond energy there is 170 kilojoules per, mole reaction for as written. So why do we care? If we're doing this, we know that this is endothermic. So, which means it's going to draw energy away from the system. So if I want to make it go faster, I would have to heat it up. Or if I wanted to use that cooling nature to something else, I could run another pipe next to it and cool down that pipe. It just, however I want to use that knowledge, I can use it to cool, or I can use it to realize I need to add more heat to keep the reaction going, because it's going to consume heat in the chemical reaction. Okay, questions with this? All right. What is the heat of formation of ammonia from hydrogen and nitrogen based off of the average bond energies. Let's see if we can figure this out. And there are the average bond energies for hydrogen, nitrogen, and nitrogen attached single bonded to a hydrogen. And I've written the Lewis structures there for your convenience. Please also note there's 3 hydrogens and there's 2 ammonias. Who are you? Who are you supposed to? Are you for Halloween or what are you? A nymph or what? Oh yeah. No, I meant, are you dressed up for Halloween?
Yeah.
What are you?
I'm gonna be a fairy because we have an event at the workplace.
Oh, cool. So I'm either link A, I'm either link B. Okay, everyone's going to B. B is correct. And I've written hints there at the bottom. You calculate that out as -80. All right, good. Guys are doing good. So now, next thing I'm going to talk about. So the last 2 topics, and you'll probably get out of here early. Average bond lengths. So when you describe a dear friend, do you say this person is a far friend or this is a close friend? Right? You say it's a close friend, and you can usually tell how close someone is, right? When you see 2 people, if you're like, like, oh, love of my life, it is agreeable to see you again, kind of thing, That's what the Vulcans say if you are a Star Trek fan. So, right, that's a whole, like, oh, I like you more than anyone else. Let's stay over there. No. When you see someone like, I haven't seen you in forever. Come on, come give me a big hug. Kind of thing. You are close. And here is basic flirting technique 101. How can you show interest in someone? You can show interest in someone by being close to them. Right? So if you're talking to someone and then you start standing closer to each other, that is usually a good sign. Of course, there's a limit to that. If you start like putting your face up against theirs, they might start to not like that, kind of thing. So, same thing the same thing works for molecules. If 2 atoms are closer to each other, they tend to be more bonded. The more bonded they are, the physically closer than they are to each other, and they can also get too close, just like 2 people. So that can be a bad thing, Why do two atoms, why do they start not getting too close? Because of their nuclei. So the positive nuclei start to repel. The electrons might say, hey, you know what? We should have a big electron party. Let's form this big orbital and we'll all hang out together. But then you can have the positive nuclei like, nope, nope, they're positive, I don't like them, kind of thing. We'll learn more about molecular orbitals next chapter. But molecular orbitals can form, and they can form a tight knit structure. But then, just like if you're seeing someone, there's a comfortable space, right? Like I can talk to somebody like, oh, you're close, I like you, we can have this conversation. Oh, you're in my face, I don't like you, kind of thing. Same thing with atoms and molecules. Two atoms, this is comfortable. Now our nuclei are starting to repel each other. Let's go back to the proper separation, kind of thing. So, all right, let's look at some of these trends. You might notice some of the smaller atoms. You look at hydrogen, right? We have hydrogen. Hydrogen is 74 picometers, and do we have another? And look at iodine. Iodine, it's 266. So, and it's both a single bond. So what's so special about hydrogen versus iodine? Iodine's a bigger atom. So it's just, that's the reason why there's more distance there. But if you look at something here like carbon single bond, 154 picometers, double bond, 134, triple bond, 120. So as it gets bonded, they get closer, right? So you're like acquaintance, friend, best friend kind of thing. So you tend to literally be closer to the people that you really like. And then you can be too close. You can still be too close, like I said. So people and molecules are very similar. And generally speaking, now this is generally speaking, the closer two atoms are, the harder it is to rip them apart. So the closer they are, they tend to be more bonded, and it's harder to rip them apart. The bond strength, this is the amount of energy you put into the bond to rip it apart. So carbon single bond, the average bond strength of this is 347 kilojoules per mole. Carbon triple bonded with itself, average bond strength 837 kilojoules per mole. That means that you have to add that much energy to rip it apart. The triple bond is closer and it's more strongly bonded, so you have to add that much energy to rip it apart. But of course, what would class be if I didn't say something and then just contradict myself right then after? And that's what I'm going to do right now. There are some exceptions to the rule here. So if you see here that we have nitrogen bonded with fluorine, chlorine, bromine, iodine. Here's the bond lengths. The bond lengths increase, but the bond strengths seem to have anything to do with the bond lengths at all. So in fact, you would think that. Actually, no. I guess you would think that the trend would be that you think, okay, so this one should be the hardest to rip apart. This one should be the second hardest. This should be the third. This should be the fourth. You can see there's a flipperoo here with bromine and chlorine, and it's just chemistry is an observational science. We can only say what we observe, and so this is what's real. So these are real data. So it's a general trend. It's not true for every single bond. So keep that in mind. So, okay. But does anyone have any questions with this stuff? Okay. In that case, we are done a little early. And we'll make this day even sweeter than class being over. It's free to eat more Halloween candy. So let me know if you have any questions, and I'm going to stop recording.